Sometimes we design systems that can suffer a power failure and the world does not end. Sometimes we design systems that suffer a power failure and the world grinds to a halt. And it's not pretty. A lot of our cloud and data center designs today simply cannot fail. But how do we service these kinds of 24/7 systems? What if we need to replace a component without turning it off? Welcome to the world of hot swapping, my friends. Hi, I'm Amelia Dalton, host of Chalk Talk. When it comes to our always-on critical systems, we need to carefully consider power protection and maintainability. In this episode of Chalk Talk, Dwight Larson joins me to investigate the issues that surround hot plugging into an energized power supply, the best solutions to consider, and what the different hot swap circuit topologies look like for a variety of applications, and why the Max 15090B and C, with its innovative current foldback startup, may be the best solution for your next design. And before we get started, don't forget to click that link. There you can find even more information about this topic from Maxim Integrated, which is now a part of Analog Devices. Hi, Dwight. Thank you so much for joining me.
Hi, thank you for having me.
Absolutely. Now we're talking about hot swap and power protection today. But Dwight, before we dig into the details, can you set the stage for us? What kind of systems require hot plugging?
Well, as you can imagine, there's a lot of systems, especially nowadays, that have to run 24/7. They can't be shut down. If you think about a data center that's processing customer orders or maybe a traffic control system, I mean, the list is endless. There's a lot of things that have to run all the time. They can't be turned off. But that doesn't mean that equipment doesn't break down or require service, right? So how do we solve that? How do we service a data center that has to run all the time but still needs to have components changed out or replaced? And that's where the ability to hot swap a assembly or a load card or a hard drive comes in. So when we talk about hot swapping something, we're talking about plugging a de-energized load device into a system that's already energized and powered up. And the way that I like to think about this is that if you are going to fill a coffee cup, right? You have a carafe of coffee. You don't want to just upend that carafe over the cup because it'll splash everywhere, and if you do it with sufficient violence, it's going to knock the coffee cup over, maybe even off the table, right? And that's sort of analogous to what happens when you plug in a de-energized load device into an energized system. You have potentially arcing or sparking at the contacts on the connector. You have a lot of inrush current to that load device because it has input capacitance, and that inrush causes voltage spikes and ringing, which can cause electromagnetic interference. And it also disturbs the supply and all other loads that are plugged into it. So if it's a server system and you plug in a new server card, maybe that voltage transient disturbs all the other cards that are already running, right? So you could have a dropout or an interruption of service. So that's no good.
Absolutely. Now, for a solution for these types of issues, what should we really be looking at?
Okay, ideally we would want a solution that would address all the issues of just plugging a de-energized load into a energized system. So we want controlled gradual turn on of power, and we want limited inrush current. We want to kind of put a clamp on the amount of current that can flow into the device. And that would guarantee that there's no disturbance of the supply or other load devices that are already plugged in. And as an added benefit, we might have the ability to stagger or sequence loads. And where that comes into play is if you go back to the coffee analogy, right, and we think about filling a lot of coffee cups, you wouldn't fill them all at once. You would fill one and then move on to the next and so on and so forth. And that is because that way you only have to manage the flow out of your carafe into the coffee cup for one cup at a time. You don't have to have a coffee carafe that can fill 20 cups at once, right? Another nice thing is if that solution could give you an indication when the load is fully energized and when the power is good and ready for loading. And that would be kind of like an indication that tells you when the coffee cup is full.
I really like your coffee cup analogy here, Dwight. But what does it really look like in a circuit?
Okay, so moving on to kind of a picture of what this looks like electrically, right? It's like it's closing a switch. This is kind of a classic problem that most engineers would have seen in college or in practice. If you just plug a capacitor or a capacitive load into a supply, you're going to get a spark when you close the contacts, and you get a sudden inrush of current because that capacitor looks like a short to the supply initially. And then the circuit forms a tank because you have a capacitor and you have parasitic inductance. It's going to ring so that the current shoots into the output capacitance, the voltage drops, Then it kind of recovers, the voltage comes back up, and the current reduces and actually flows backwards, and you get ringing. And that ringing is bad because you get a high voltage transient and a low voltage transient that repeats over and over again until the energy is lost in the parasitic resistance. And that causes all kinds of problems with the load, it causes problems with the supply. It's just bad all around.
That definitely makes sense. Now, a simple solution here would be to use a resistor, right? But that doesn't solve all of our problems.
Exactly. So if we, again, extending the classic electrical engineering problem of connecting a voltage source to a capacitor, the way to solve that is to damp it, right? We could put a resistor in series, which would give us a damped response. We'd have less inrush current, and we'd get rid of the ringing, but there's a couple of drawbacks to it. There's some shortcomings here. The first is that the voltage rise is sort of an exponential decay function. What I mean by that is that it's a 1 minus e to the minus t over tau. So you get an exponential rise towards an asymptotic point. Maybe we could live with that, but the real big problem here is that now we've inserted a resistance in series with the supply and the load, right? So any current that flows to the load has to go through that series resistance, and we end up with a lot of power loss, which obviously is no good, especially when you're talking about tens or hundreds of amperes.
So, Dwight, what would be a better solution than adding a resistor?
Well, conceptually, we could add a current source in series with the supply. And this solves all the problems that the resistor solves because it limits the inrush current. And now we get a nice linear voltage rise because of the capacitance and voltage relationship, which is I equals C dV/dt, or dV/dt is equal to I over C. And that means that the slew rate is the current over the capacitance. In this case, if we have a constant current source, then I is constant. The output capacitance is a fixed value. So you get a constant slew rate for the rising voltage on the output. And that's shown in my plot on this slide. You can see that the output voltage rises linearly, eventually it reaches the input voltage, and then it's fully turned on. And our inrush current is a constant current, basically a step to a constant current. And then when the startup is complete, then it settles down to the Vn over the load, the running current. So this is a really nice solution. And the other nice thing about this too is that if we size the current source to be appropriate for the supply we have, then the output current can't exceed the supply capability. So adding a current source in series, conceptually it's simple, but how do we do it in practice? Well, the way that's typically done is by adding a switch element, which would be usually a MOSFET transistor, in series with the supply, and this becomes our hot swap circuit. Now to make that into a current source, what we want to do is operate that MOSFET as a source follower. So we drive the gate of the MOSFET with a current source, and we refer it to ground through a capacitor, which is shown as C gate in my slide. And then we charge that gate capacitor with a constant current source. And that gives us, again, an I equals C dV/dt relationship. So we have a fixed slew rate at the gate of the transistor. And because it's a MOSFET, the source of that MOSFET will follow the gate -1 gate to source threshold voltage. So once the gate reaches the point where the MOSFET starts to turn on, the output voltage rises, and it really can't rise any higher than the gate voltage minus the gate to source threshold voltage. So they track each other. The gate voltage rises linearly, so does the output. And because we have a fixed slew rate on the output, we have a constant current inrush. So this is a really nice solution. It gives us all the things that we want. We have controlled slew rate, linear voltage rise, and a constant inrush current. And it's a realizable circuit, right? This is something we can actually build in an integrated device.
Fantastic. Now, does this type of circuit work for all applications that require hot swapping?
There are similar circuit topologies that will be used for other applications. The circuit I just showed, which is a high side N-channel solution, is very common for 12-volt systems, 5-volt systems, things like that. The reason for that is because an N-channel FET typically has very good performance for its size and cost. However, there are also applications where we may use a high side P-channel, and the advantage there is that we don't have to have a charge pump anymore, right? We can simply pull the gate of that P-channel FET below the input rail and turn it on in a controlled manner. And the other thing that we might see is in telecom systems or systems where you have a negative supply voltage for corrosion and reasons like that. That comes up in telecom a lot. We might have a low side N channel switch, which is sort of analogous to the high side P channel switch because now we enhance the FET by pulling the voltage up from the minus rail to a voltage in between ground and the minus rail. So those are the three common circuits that you'll see for hot swap, and they all function kind of similarly. But the one that I want to talk about most today is the high side N channel.
Okay, great. Now, are there any other possible benefits here?
Yes, absolutely. Because we've put a switch element in series with the supply and the load to control inrush during startup, it also gives us a really nice thing, which is we can now protect against overcurrent or a load fault. Like let's say that the device we plug in fails in some way, right? The hard drive motor fails with a short, or there's an input capacitor that goes bad in a server rack unit. Now that switch can be used to disconnect that failed load. And the way we do that is we have to have some sense of what the load current is, and then compare it against a predetermined safe limit. And if we exceed that, then we pull down the gate of that FET and switch off the power to the load. So it becomes a electronic circuit breaker or electronic fuse, if you will.
Okay, but how do we measure current in order to have protection functions?
Yeah, as I mentioned, in order to do this kind of electronic circuit breaker function, we have to have some awareness of what the current is. Now, the simplest thing to do, I think, is to put a resistor in series, right? A small resistance value, nothing as large as what we talked about earlier on to limit inrush, but a simple, small current sense resistor, something in the milliohm range that would give us a measure of the load current, and we can run that into a current sense amplifier and then compare it against a threshold, and that would give us the ability to detect overcurrent. Now, there's a drawback to that, which is that we are adding resistance in series. So how could we solve that? How could we take out that added sense resistor power loss? Well, we have a MOSFET switch already, so arguably you could sense across the MOSFET because the MOSFET, when it's fully enhanced, has some on resistance, RDS on. You could sense across that, and it would work very well once the MOSFET's enhanced. But there's a couple of drawbacks there too. First of all, it doesn't work when you're turning the device on, right? So during the initial power up, you can't really sense current during that time, and that's obviously a time when you'd have to be protecting against faults as well. And the other drawback is that MOSFET RDS on can vary, right? It varies from device to device because it's not a controlled parameter. And also it varies with temperature, right? So it doesn't give you a very precise measure of current. But you will see some low-cost devices measure across the MOSFET RDS on. Now, there is a further improvement that can be realized when you have an integrated pass FET. You can allocate a portion of the pass FET area to form a current mirror circuit. So the lion's share of the current flows through the large area of the MOSFET from supply to load, but then you also have a small area of the MOSFET that is a current mirror, and that gives you a scaled version of the load current, which you can then use to compare against a threshold and provide overcurrent protection. And the beauty of this is that you don't have to add any resistance in series, and you don't have any losses because of that added resistance. And also it's a very precise technique. You don't have to worry about the RDS on TEMPCO or part-to-part variation because it's the current through the large portion of the MOSFET and the small sense portion is proportional to the area, and it's a very precise relationship.
That makes sense. Now, Dwight, what does Maxim offer in terms of hot swap and power protection?
Maxim has a part that I'd like to talk about that's a very good example of high-side N-channel hot swap and power protection with an integrated MOSFET, and that's the Max 15090B and Max 15090C. And these are a hot swap solution for 2.7 volt to 18 volt rails up to 12 amps. So Maxim's solution does all the things that we want from a hot swap. It controls the turn on of power. It can detect and isolate faults, in other words, work as an electronic circuit breaker. It also can report the load current. It actually has a current sense amplifier output. So in addition to measuring the current for its own electronic circuit breaker protection function, it can actually generate a signal to the outside system. So you can digitize that and feed it to a system management microcontroller, etc. So that's a very nice feature. And it provides ease of design and space savings because this is a very small IC. It's only 7.3 millimeters squared. So this device is monolithic, which means that the pass FET is integrated. There's no external MOSFET to choose or build into the circuit, and there's no sense resistor. Everything is in one IC, and that gives you very high power density. You have a 12 amp solution that is, as I mentioned before, only 7.3 millimeters squared, and it has low RDS on, only about 6 milliohms on resistance in that pass FET. So this is a great solution for servers and storage, networking and communication equipment, and potentially also for consumer electronics.
Okay, cool. Now, Dwight, what does this actually look like on a PCB?
As I mentioned before, this is a really small device. It is a WLP package, which is a wafer-level package, and it attaches to the PCB through an array of bumps. It's 4x7 array on 0.5 millimeter pitch. 11 of those bumps are signal bumps, in other words, things like the current sense signal, the enable signals, things like that. And then 17 of the bumps are the power path bumps. So we have in and out and ground. And you can see an example of that pinout in this slide here, as well as a picture of the EV kit for this device. And the Max 15090 is that small rectangular device in the middle of the board there. So you can see that it's very small in relation to external components and such. So it's really a great solution if you are space constrained.
So Dwight, what does this look like in a schematic?
So the Max 15090 BEV kit schematic is shown here, and it's an EV kit, so there's a certain amount of components that are included for ease of evaluation. Really, when you design this into a circuit, you just have to have output capacitance and components to set the gate slew rate and the circuit breaker limit. In the EV kit, we actually have obviously input and output jacks. There's a bypass cap for the regulator, which is the internal bias voltage. And then most importantly, I think we have the circuit breaker resistor. The way that you set the circuit breaker limit in this part is by tying the CB pin to ground through a resistor. And that resistor value can be up to 40.2K. And at 40.2K, then the current limit for the part is 12 amps. And you can go lower to scale the current down. In the EV kit, we do that by running the CB pin into a jumper, which can either go to a 40.2K ohm resistor, or it can go to a potentiometer so that you have basically infinite adjustment of the circuit breaker setting resistance. The part also has separate UV and OV inputs, and these are connected through a resistor string, 3 resistors in a divider configuration. The high point of that divider is taken to the UV pin, and the low point is taken to the OV pin. And the idea is that as the input voltage comes up, the UV pin rises above its rising threshold, and the part is enabled. But if the voltage rises too high, then the OV pin goes above its threshold, and the output is shut off. So you have undervoltage and overvoltage protection. Now, in addition to that, there's a watchdog input, if you want to think of it that way. It's the enable bar input. And this is not a typical enable signal that would turn on the hot swap. What this is a signal that comes from the load device, and it's expected to go low within a certain time period after the output is established. So in this way, the load device can actually handshake with the hot swap and say, yes, I'm up and running, everything is good, and it will pull that enable pin low and keep the hot swap turned on. If the Max 15090 B or C doesn't see that, if the enable pin doesn't go low within the allowed time, then it'll actually turn off the power and cycle it. And so it can give you the ability to restart a load that didn't start up correctly. And as I also mentioned too, we have a fault output, which can indicate if a overcurrent fault occurs. We have a power good output, which indicates that the output is up and ready for loading. And we also have that current sense output, which is iSense, and that can be brought out to an external ADC.
Okay, so can we get into a little more depth here? What does the Max 15090 OB/C really buy me as an engineer?
So the Max 15090 B and C block diagram shows what's in this IC, right? Like what you get in this device. As I mentioned before, there's an integrated pass FET. Up near the top of the device, you can see that. And you can see also that the portion of that pass FET that's used for current mirror is shown there as well. The signal from that is brought down to our circuit breaker comparators and also to the current sense amplifier output, etc. You can also see the window comparator for the UV and OV inputs, which give us our undervoltage lockout and overvoltage protection. You can see the gate pin is brought out to the outside, and that gate pin is charged by a current source. So the value of capacitor that the customer or user connects from gate to ground allows us to set the initial voltage slew rate for the output startup. We have a C delay capacitor input, which sets the timer for that enable bar input, which is like a watchdog handshaking input. And we also have the CB pin, which goes to a resistor to ground, and that's driven by a 12 microamp current source, and that establishes the threshold for overcurrent protection. And then finally, you can see that we have the power good and fault output, which are both open drain outputs.
So Dwight, what benefit does current foldback provide?
One feature that the Max 15090 B and C has that is not seen in every hot swap device is something called current foldback startup. Now, when I was talking about this hot swap solution, we talked about the fact that we want to have a current source in series with the supply to the load. We can have a constant current source, or in the Max 15090 B and C, we actually have an innovative feature, which is foldback startup. And what this means is when the voltage across the device is high, in other words, you plug in a de-energized load, and the input is at maybe 12 volts, and the output is at 0 volts, you have a high voltage across the pass FET. At that time, we actually allow a small current to flow through the device. And you can see that in this plot here. It starts at 1 amp, and it remains at 1 amp until the voltage across the device drops to 10 volts, at which point the current is allowed to begin to increase. And so the current actually follows along that foldback path increasing as the voltage across the device decreases. And eventually, at the point where the input minus output is 2 volts, then we clamp at 6 amps, and that again is a constant current source. So the advantage of this Foldback startup is that it can accommodate a wide range of load resistance and capacitance. And I actually have an example startup shown here. You can see that the Vout rises not in a straight line, but actually has a little bit of curve to it, and that's because the current is changing according to that Foldback startup characteristic that we showed before. If you remember, we started at 1 amp when the voltage was high, and then we increase linearly up to 6 amps when the voltage across the device is fairly low. And if you look at the I-out plot, you can see that we start at 1 amp, and then around 10 milliseconds, the voltage across the device has decreased to about 10 volts, and we begin to rise. The current increases and rises up to 6 amps and clamps there. During that time, the average inrush current is 2.473 amps, and I measured that by averaging my values in a calculator spreadsheet. Now, the power of the MOSFET is also modulated by this Foldback characteristic. It starts fairly low at about 12 watts, and then at 10 milliseconds or so, when the current is allowed to begin to increase, we can see the power in the device actually increases up to a peak of about 21 watts. And this is the power that's dissipated in the switch during startup. And accordingly, the temperature in the junction rises. This is the temperature of the actual pass FET. It begins at the ambient temperature of 50 degrees C, and then rises as the startup progresses until it reaches about 120 degrees C, at which point the MOSFET's fully enhanced and the temperature starts to drop off because now we only have I squared R loss, the load current, times the RDS on the pass FET. So the device would actually cool down quite a bit until it's close to the ambient temperature again. So I want to contrast this with a simple constant current startup. If you recall in the previous case, I said that the inrush current averaged 2.473 amps. So what happens if we have a constant current startup where we just fix the current at 2.473 amps? Well, in this case, with the same load conditions, which is a 3 ohm load and I think 3,300 microfarads capacitance, you can see that the part actually can't start up because that constant inrush current is not adequate to charge the output cap and supply the load. If you think about it, if we have a 3 ohm load, at some point the output voltage is going to rise to the point where we have 2.473 amps flowing through the load resistance, and there's no longer any current left to charge the output caps any higher. So the output rises to that point, and then we can't charge the output caps any higher. It never finishes the startup. So this shows why the Foldback is advantageous, because the customer or user can put the part on the board, select the circuit breaker limit that they want for normal operation, and then the startup is kind of taken care of automatically. It will allow enough current to charge the output capacitance and supply the load without having to do a lot of calculation up front to figure out how much constant current is safe, etc. So the advantages of that Foldback startup then are the ease of design, the fact that you can pick a circuit breaker limit and the startup is taken care of automatically. It accommodates a wide range of output capacitance and load characteristics, right? So it doesn't matter if we have a resistive load or maybe a switcher that has a negative impedance characteristic. In general, the Foldback startup will get that load powered up and running without the designer having to worry about safe operating area for the MOSFET, because we've taken care of that with the Foldback characteristic. So the way we get this result is because the Foldback characteristic smooths out the MOSFET power. It avoids high peak power dissipation. It reduces the peak inrush current compared to a constant DVDT startup. It's more flexible and safer than a constant current startup. And because Maxim defines the Foldback characteristic for our own integrated MOSFET, we can respect the safe operating area at all times. In addition to that, I want to mention that Maxim can provide a spreadsheet calculator to model almost any startup condition.
Great. So you guys have solutions that bridge a wide range of voltages, right?
Yes. So we've talked about the Max 15090 device, which is a 12 amp hot swap solution. But you can see that Maxim also has a full portfolio of hot swap devices, ranging from 6 amps up to as much as 120 amps. Now, the devices from 6 amps to 15 amps feature the current Foldback startup that we talked about, and the devices above that range, from 30 amps to 120 amps, use a constant DVDT startup, but they also feature PM bus. And PM bus is a serial bus that allows the system to communicate with these hot swap devices and get digital telemetry information. In other words, they can read the output current, the input and output voltages, the device temperature, and they can also check the device status. They can look for fault and warning flags, and also shut down and re-enable the parts through that serial interface. In the higher current parts, from 30 amps and up, you'll see that to do a 60 amp solution, we have a single device, the Max 16545B. If you want to extend that to 90 amps, you can pair it with the Max 16543 follower device, which is not a standalone hot swap, but it can be paired with the Max 16545B in sort of a controller and follower device configuration. And you can add as many as 2 of those follower ICs to go up to 120 amps in this chipset solution.
All right, well, Dwight, I think that's all I have time for today. Thank you so much for joining me.
Thank you for having me on Chalk Talk. It's been a lot of fun.
And before we go, you didn't forget to click that link, did you? There you can find even more information about this topic from Maxim Integrated, which is now a part of Analog Devices. For Chalk Talks, I'm Amelia Dalton from eejournal.com. For more Chalk Talks, head on over to the Chalk Talk section of EE Journal. You can't miss it. It's right across the top. Or head on over to YouTube, youtube.com/EEJournal.